If someone claps across the room, their hands never touch your ears, so how does the sound reach you?
Seriously, think about it for a second. The person who made the sound is way over there, but your ears are, well, over here. There's nothing visible traveling between you, right? I mean, the air doesn't suddenly rush all the way across the room like a thrown baseball. So what exactly is crossing that huge, seemingly empty space to get to your ears? Let's solve this mystery in today's explainer.
Okay, so the secret here is actually an invisible chain reaction. Every single sound you hear goes through 4 amazing steps. First up, it starts with a vibrating source. Maybe that's clapping hands, a plucked guitar string, or even a ringing bell. Second, that source makes the tiny invisible particles right next to it vibrate. Third, that vibration is passed along, literally jumping from particle to particle. And finally, step 4, that passing vibration reaches your ear, where your eardrum detects the sound. Let's zoom in on that very first step for a minute. What exactly is a vibration? Well, a vibration is just a repeated back and forth movement. When a sound source vibrates, like say your vocal cords when you're speaking, it pushes and pulls on whatever is right next to it. Actually, try this. Gently touch the front of your throat while you talk. You can actually feel it. It's pretty cool. Even if a vibration is way too small or too fast for our eyes to see, it is absolutely always there, kickstarting the whole journey of a sound.
So, the source is vibrating, it's pushing and pulling, but what are the tiny, totally invisible particles in the air actually doing? How in the world do they carry this vibration all the way across the room to your ears?
Okay, we need to clear up a really common mistake right now. A lot of people think that the air particles right next to the clapping hands fly all the way across the room and shoot directly into your ear, kind of like tiny invisible baseballs. But no way. That is not what happens. The reality is actually much cooler. Individual particles mainly just vibrate back and forth locally. They don't go on some long, epic journey. They pretty much stay right in their own general area.
So instead of flying across the room, particles pass the disturbance to their neighboring particles. Think of it like a massive stadium wave at a football game. You know how it works. The people in the stands stand up and sit down in their own spots. They don't run all the way around the entire stadium, right? That'd be crazy. But the wave, the energy, travels all the way around the crowd. That's exactly what air particles do. They give their neighbor a little gentle push. That neighbor pushes the next one. And the sound energy travels forward while the particles just hang out near their own spots. All right, let's shift to a completely different scene. We know the stadium wave effect works in the air, but what if you're swimming underwater? If someone taps 2 stones together down in the pool, will we hear it through the water?
The answer is absolutely yes. And this brings up a massive scientific idea. Sound needs a medium to travel. And a medium is really simply any matter made of particles. Air is a gas, water is a liquid, and a table is a solid. The big thing they all have in common? All 3 of these states of matter are made of particles. And because they have those particles, they can all carry sound vibrations. I mean, dolphins and whales rely on this entirely to communicate underwater.
Now think about how these particles are actually arranged, because this changes everything. In a solid, like a wooden desk, the particles are packed very, very closely together in a fixed structure. In a liquid, like water, they're close together, but they still have enough room to kind of slosh and move past each other. And in a gas, like the air in your room, the particles are much farther apart and just move around freely.
So, knowing how these particles are packed, which material do you predict will carry sound best? If I tap a pencil, will you hear it more clearly and quickly if the sound travels through the open air, or if you press your ear right against a solid wooden desk? If you guessed the solid desk, you hit the nail on the head. Here's exactly why. In solids, the particles are closely connected and packed super tight. Because they're basically shoulder to shoulder, vibrations pass very effectively and very quickly from one particle to the next. It's exactly like a row of falling dominoes placed right next to each other. Boom, boom, boom. But in gases, the particles are much farther apart, so it takes a bit more time for them to travel and bump into their neighbors. The totally crucial point here is, sound generally travels fastest and is transferred very effectively through solids.
But wait, what happens if we go out into outer space? Space is mostly a perfect vacuum, and a perfect vacuum means absolutely no particles. And if there are no particles, well, there's nothing to pass the vibration along. So, perfect vacuum equals no particles, which equals no sound. You could literally explode a massive firework in a perfect vacuum and it would be completely silent. Crazy, right? This is exactly why astronauts have to use radio systems to communicate. Ordinary sound simply cannot travel without particles.
So, we've explored solids, liquids, and gases.
But how do scientists actually prove which material carries sound best? How can we make this a fair test like a real scientist? Let's say we want to test the ticking clock through air, water, and wood.
We have to be very careful here. An unfair test would be changing the material and the distance at the exact same time. Imagine testing a quiet clock from 10 feet away in the air, and then testing a super loud alarm clock right next to your ear on a solid desk. You wouldn't have any clue if the sound was louder because of the desk, the distance, or the new clock. A fair test means we change only one main factor to make a trustworthy comparison.
That one factor we deliberately change, it has a special name. It's called the independent variable. An easy way to remember it is, I change the independent variable. In our investigation, we are deliberately changing the material the sound travels through. First air, then water, then a solid table. So the material is our independent variable. Once we change our material, we need to actually measure the result. And this is the dependent variable. It's what we observe or measure because of that change. In our test, the dependent variable is the sound level we measure when the ticking finally reaches us. You might see a tool measure this in units called decibels, but for us, we're really just looking for how loud it gets. And to make absolutely sure our test is completely fair, we have control variables. These are all the really important things we must lock down and keep exactly the same. We have to use the exact same sound source, the exact same distance, the same measuring method, and the same room. By keeping all these locked in, we know for sure that any difference in our measurement is strictly because of the material we tested. It's like a giant puzzle, and we're controlling all the pieces.
Okay, let's dive into our results. Notice how we didn't just test it once. Scientists always repeat their trials to make sure the evidence is actually reliable. When we check our results, the air gave us a sound score of around 40 decibels. The water was higher, hovering around 55. But look at the solid table. The readings jumped right into the low 70s. Because our test was fair, this evidence confidently shows us that the sound was transferred most effectively through the closely packed particles of the solid table.
All right, it's time for a rapid-fire challenge. Based on everything we've just uncovered, let's think about air, water, and a solid table. Can sound travel through all three?
Yes. Air? Yes. Water? Yes. Solid table? Yes. But what about a perfect vacuum? That's a hard no. Remember, the first three are states of matter. They contain particles that can bump into each other and pass those vibrations along. But the vacuum? It's totally empty. And this brings us to the ultimate golden rule to remember from this explainer. Sound needs particles to carry vibrations. Whether it's the air you're breathing, the water in a swimming pool, or the solid wood of your desk, the magic of sound is really just energy dancing from one tiny particle to the next.
So, we've totally solved the mystery of how sound travels to our ears. But here's a brand new mystery for you to think about. Two sounds can travel through the exact same air, but one might be a tiny, quiet whisper, and the other might be a massive roar that shakes the whole room. Why are some sounds loud while others are so quiet? Well, we're going to figure that out next time.